Welcome wherever you are, and also those who are attending for the first time. Welcome to this webinar series. For those who are rejoining after the first webinar, thank you for coming back again. Let me introduce again the Thai office who is in charge of organizing the webinar and also the demonstration presentation session of the software. We have Orakoch, who is the project manager. Then we have Nichakon, Jakrapat, Konkanok, and Siripon, who are looking after different aspects of the PSC for Speed company. And they are also the hosts for these webinars. As I said, webinar 1 was in 3 parts, 14, 15, 16 July. Today, we are doing webinar 2, which is property estimation in 4 steps. And because of requests from our Asian participants that we were ending too late in the night for them, so we advanced the webinars from 13:00 European time. This will be for all the webinars. And just to advertise, the next 2 will be in August, 16th August and 25th August on refrigerant design selection verification, chemical substitution, and then the final 2 in September, 9th and 16th, on product design and model development. And we plan to repeat every year between July and September this kind of webinar series, but the topics will be different. So the objective of this webinar, that is webinar 2, is to give the participants a view of property estimation in terms of types of properties and their models, when properties are needed and their roles in process product design and analysis, and how to use the property models through a systematic computer, through a set of systematic computer-aided tools. So use of a systems approach that we also see in webinar 1 will play an important role. We are not expecting you to make a expert in property prediction in one webinar. What we are planning to give you are some background information that will help you to not only calculate properties, estimate properties, but also use models and use simulation tools that estimate properties more efficiently. So the schedule of the lectures is that first, I will give you an introduction to properties, highlighting when, what, why, and how, not in the same order. And then the last part of that lecture will be about modeling and estimation of what we call primary and secondary properties. The next lecture will also be given by me, which will be about phase equilibrium calculations and models used for that. The third lecture is going to be given by Professor John O'Connell, who is our guest speaker for this webinar. He will give you some theoretical background on the fundamentals of property model applications. So my lectures will not be too much theory, a little bit of theory, more about concept and background. And the final session, which actually is 4, not 5, will be given from the Thai office by Orakoch and Konkanok on the use of ProCape, which is our software tool. So if you need some background information, I will also highlight these books. The book that you see, Computer-Aided Property Estimation for Process and Product Design. A lot of the material is actually coming from different chapters of this book. Also, first let me talk about the paper, a fluid phase equilibrium paper from 2006 mathematical and numerical analysis of property models. A lot of the information from this paper is also going to be presented. And there was in 2018 a special issue of fluid phase equilibria with about a number of papers on property prediction, on modeling, on experimental data, all of it as a collection to honor Professor John O'Connell's contribution to fluid phase, to thermodynamics. And that also has a lot of useful information. Also on slide 38, the last slide, I've put some additional references that may be interesting. So let me start with the role of properties. When I say properties, I mean actually property values, which are coming from database data or models, okay? So when I say properties, I mean values obtained from data and or models. So let's say that we have a chemical process shown in the flow diagram below. There are reactors, there are separators. What is happening in that chemical process is that there are some chemicals that are being converted either from reactants to products or being separated. Some operation is involved with these chemicals. And any operation with these chemicals means that the properties of these chemicals, just to give you a list, melting point, boiling point, critical pressure, critical temperature, heat of fusion, pressure, vapor pressure, all of these, the way those properties change or the way the molecular structure have these properties change the process and the operation of the process. So if we are running the process, then we can see that those chemicals will behave in a certain manner to affect the operation. But if we want to see it in a, let's say, in a model, in a simulator, for example, the simulator will have mass balance, energy balance, it will have some constraint equations, and the bottom set of equations, constitutive equations, are the property models. And these property models are also embedded in the mass balances. So which means that if we have a model for all these properties and we can calculate the properties, we can do the simulation. And through the simulation, what is popularly known as digital twins, we can create a digital twin of the process and look at how the process is working under different conditions. So properties then is at the heart of the model and the process, whether the process is real process or whether the process is digital twin, the properties will affect them in the same way. Now, can we have a model that will represent the reality? That is what we will see and how to do that. So let's understand the role of properties in terms of process engineering. The first role I say is a service role. And before I explain the service role, let's look at what, in terms of process synthesis design, all the topics that we covered in webinar 1, how the properties affect that. If we are doing synthesis, properties help to identify the feasible alternatives. If we are doing design simulation, properties help us to identify the exact condition of operation in terms of temperature, pressure, composition that gives a property value that satisfies our design criteria. And the same properties, if we want to look at their effect with respect to changes in temperature, pressure, composition, then we would be able to design a better control system because we are controlling the temperature, pressure, composition. So the sensitivity of the properties to the changes in temperature, pressure, composition help us with control and design. Then if we know the composition, the phase state, the temperature, pressure, we can do the energy balance. If we know the compositions, we can calculate the environmental impact properties and evaluate the environmental impact. And the temperature pressure composition also affects the capex and opex, so we can also do the economic analysis. So we can see that properties help us in all those aspects that we talked about in webinar 1. So then what is the service role? This is the most common role of properties that people associate with, and probably that's why sometimes they don't respect the property thermodynamics that much, because what happens here is that whether it's the designer or the simulation model, if a property is needed to make a decision, one says, okay, I have this compound or a mixture of compounds at this temperature and pressure, I need a density, or I need the heat of vaporization. And then the property model gives that value. So that's what I call a service role. And that is the most common role, because whether it is in a simulation or whether it is in a design, we just say describe. It's not moving. Okay. We just describe what is our problem in terms of which compounds we have, what is the temperature pressure composition. We go from the model, from the simulation model to the property model, giving this information, and we get back the properties we want. So that's the typical service role. But properties actually can play more important roles, as we will see now. So we have already seen what properties can do. And what I would say is that in addition to service role, properties can also advise. So for example, if we want to separate a mixture by solid liquid equilibrium, we want to put an anti-solvent that will create a solid phase. But which solvent do we need? And what properties do we need? And what property values would tell us whether that solvent would be feasible for solid liquid separation? So one can see that through the property values, thermodynamics can also tell us whether the operation we want to do is feasible or not, as well as what should be the target value for that operation, even what should be the anti-solvent. So again, here we not only give the composition, temperature, pressure, we do the opposite. We say that we want to solve this problem and we want to know whether solid liquid extraction will be feasible. And then the system will find out the solubility and other properties and say whether it will be feasible or not. So here we are advising in addition to giving the service role. But if we advise, then the service role becomes a verification, because the thermodynamic properties will say, yes, this solvent is good because it has a solubility of this value. And then we do the service role to check whether that advice was good or bad. Is there more thermodynamics can do? What I would say is that it can even help us to solve the problem, which means that if we have the values of the properties and we also have the advice role, maybe we can even get help from thermodynamics to solve the problem. And especially when we have phase diagrams and things like that, it actually helps us to solve the problem. So let's see an example. Again, we can see the service role at a given temperature for a given compound. What is the vapor pressure? That's the service role. For a mixture of compounds, if we want to separate by distillation, the advice would be if the binary mixture of compound form azeotrope, then distillation, single distillation, conventional distillation would not be feasible. If the azeotrope moves with temperature, then pressure swing distillation may be feasible. So this is the advice that thermodynamics can give us. Can it help us to solve the problem? As you have seen in webinar 1.2, that if we convert the phase diagram, PTXY diagram, into a driving force diagram, then that driving force diagram will help us to find the optimal design of the distillation column without actually doing too much calculations and doing optimization. So, because at the maximum driving force, if we calculate everything, all the design parameters of the distillation column, by definition, it will require the minimum energy. So what we can see is that thermodynamics not only plays the only well-known service role, but it also plays advice and solve roles, and we need to use more and more of this. So with this as the background, let's look at the classification of properties. So on the left, you see chemicals, and chemicals then converted into products. On the right, you see operations where chemicals are involved. So what are the properties? The text highlighted in yellow are the fundamental basic properties. Some of them affect the process, some of them affect the product. And then some other properties, like in the white box, which are called the process function and product function, they affect the operation of the process, or they affect the performance of the product. And then through those properties, we can design the process or the product. So at the heart of the model for the process or the product, we have the models and data of properties, and these are the phenomena, which is the thermodynamics, reaction kinetics, phase transfer, all of these defined by their properties. The challenge and opportunity is to understand how chemicals behave in processes and products. So let's see what kind of chemicals are involved and what kind of properties are involved. We can talk about simple compounds, refrigerants, but also I'm not showing hydrocarbons. Hydrocarbons will also be there everywhere. Solvents, organic solvents, ionic liquid solvents, active ingredients, a little bit bigger, lipids and surfactants, polymers, oligomers, and as I said, hydrocarbons, which are not shown, but hydrocarbons are everywhere, so also hydrocarbons. So what do we need of these chemicals? We need to understand the properties that define the phase state. Is it vapor, liquid, solid? And what is the pressure, volume, temperature relationship? Properties that define the feasibility of an operation, like if it is distillation, what is the vapor pressure? Properties that define the process operation, what is the effect of temperature on the vapor pressure? Properties that are needed for equipment sizing, for example, what is the density, so that we can calculate the volume of the tank. And finally, properties that affect environmental health, safety, all those properties. And there can be many more. What we see is that when the size of the molecule is small, it is usually easier when to estimate the properties, and more properties are available, measured data are available. When it is bigger, it becomes more and more difficult. So what are the properties that define the phase state and pressure, volume, temperature? These are boiling point, melting point, pressure, volume, temperature relationships, which are affected by critical temperature, critical pressure, eccentric factor, and many others. What are the properties that define the feasibility of an operation? Equilibrium constants, transfer coefficients, azeotrophs, phase boundaries, functional properties that change with temperature, pressure, composition, like enthalpy, entropy, density, vapor pressure. Then density, volume as a function of temperature, pressure, composition. thermal conductivity, diffusivity, solubility, and then environmental, health, safety properties. Those are all affecting the feasibility of an operation, because if the operation is feasible, we want all of the values to be as we want. If we want to look at define the process operation, then after we look at the feasibility, we set the values. This should be the transfer coefficient, this should be the phase boundary, this should be the enthalpy, this should be the entropy. So we fix the values for at a certain condition. So that is defining the process operation. Equipment sizing, these are the sizing parameters that affect the density. Volume will affect the size of the tank. The thermal conductivity will affect the area. The diffusivity will affect the area for mass transfer. Solubility will decide how much solvent is needed, and so on. And then finally, the environmental health safety, the global warming potential, ozone depletion, toxicity, exposure limit, flammability, auto-ignition temperature, and many more. Those will help us to study the effect of environmental health safety and so on. So these are the properties we need. So if we need these properties, we will then see how we can classify them in such a way that modeling would be easy. So the challenge opportunity here is which model to use and/or how to measure the properties. So we define the properties that you see on the left-hand side into one, which we call the primary structural properties. These are the pure compound properties of any molecule. And the good thing about that is that it is only dependent on the molecular structure of the chemical. So every chemical defined by its molecular structure has only one value of this property, not anymore. So then molecules can be classified very easily through these properties. Then the next, I think I've mistyped here. This should not be what I'm talking about as functional properties here. It includes also the secondary properties. So these are pure compound properties. At a given temperature, they can be calculated from other properties. So that's what we call the secondary properties. And then the functional properties would be that what would be the vapor pressure as a function of temperature, heat of vaporization as a function of temperature for still the pure compound. And then the next one, the third one, let's go back. This one is we have fixed the temperature, pressure, and composition. So we have a mixture. We know the temperature, pressure, composition. We just want to know the properties of this mixture. And it is not in two phases, it is in single phase. And then the last one is that we do not know the phase. It can be in two phases or more. So we want to know the equilibrium properties of the mixture as a function of temperature, pressure, composition. And the equilibrium properties are usually gamma, which you see the first one, and the fugacity, which is the second one. And then we need to know whether the phase is liquid or vapor. So activity coefficient in the liquid phase for every compound, fugacity coefficient in the liquid phase for every compound I, or fugacity coefficient I is missing there for the vapor for every compound. So these are then the properties we need. And so just to summarize, we have the classification of the properties: primary, secondary, functional. Functional can be pure compound functional, mixture functional, and phase equilibrium functional. And then we have the primary and we have the secondary. And we want to know why properties are needed, when properties are needed, which properties are needed, and how the needed properties are obtained. So with this as the introduction to the lecture, the remaining period of this lecture, I will talk about pure compound property modeling. Then in lecture 2, mixture and phase equilibrium properties. Then lecture 3, fundamental property model applications by Professor John O'Connor. And then from the Thai office, Orakoch and Konkanuk will talk about or will demonstrate and problem solution through ProCape. So the property modeling that I'm going to show for pure compound properties, primary properties, is using the group contribution approach. So again, I'm showing you the classification of the properties and the kind of properties. Now I will introduce you to the classification of the models that can handle this kind of properties. So if you look at estimation methods, in my opinion, there are two types. First, the one on the left is reference. And reference means that these are highly accurate property values if we can obtain them. And because we can obtain them, if we can obtain them, they become almost like a experimentally measured data. So that's why we call them reference. And these kind of models can come from first principles or mechanical models like quantum mechanics, molecular simulation, but they also have to be verified that they are correct. The good thing about them is that the perfect mechanical model should not need any parameters. From the first principles, we should be able to predict them. So there are models like that can take a long time to predict the value, but if we can verify that the predicted value is good, they are good as pseudo-experimental. But most of the models, because they need parameters, I would call them approximate. They do not apply totally to the theory. And among the approximate, there are empirical, which just fits the data, chemometrics, pattern matching, factor analysis, QSAR are examples of them. What I'm showing is not the only models, just some of them. So empirical models is on one side, reference model is on another side. In between is what we call semi-empirical models, equations of state, corresponding state theory, topology or geometry-based models, group contribution that we will talk about, atom contribution, bond. So the idea is that if we have groups or atoms or bonds and they contribute to the property of a molecule, then adding all the contributions, we should get a good value of the property. And then you can think of, if we have infinite number of groups, then we will have an exact match. Of course, we cannot have infinite number of groups. So if we have limited number of groups, we cannot be exact. So it will be approximate. So what are the methods, models used for different kinds of properties? So we can see, and this webinar will highlight these for primary properties and functional phase equilibrium properties. We will highlight the group contribution approach and also equations of state. But these primary properties can also be obtained from molecular modeling as well as direct data fitting. For secondary properties, usually corresponding states theory are used and also direct fitting of the data. For functional properties, almost everything is possible. But if we want predictive models, we should go for group contribution type of models. If it is empirical, it is not usually predictive. If it is quantum mechanics, it can be quite difficult and needs to be validated. So the easiest is I didn't put the equations of state in the middle, or corresponding states theory. So if we go back here, we can see that we want to make approximate models, which are semi-empirical models. And in semi-empirical models, we will have parameters. In order to estimate parameters, we will need a database of measured data. So in order to develop a model, we need data, we need model equations, and we need to regress the parameters. So we need databases. What kind of databases? All kinds: chemicals, solvents, additives. There are all kinds of data that are available, and chemicals can be classified, so we need databases. And then we need model types. As I said, we have models for pure compound property, primary property, secondary property, functional property for the pure compound, and for mixture property, bulk, and phase equilibrium. And having the model is not enough, because if we want to do phase equilibrium, these models have to be put in a calculation sequence. So the calculation sequence has to find out at what conditions of temperature, pressure, composition, solid-liquid equilibrium will exist, or vapor-liquid equilibrium will exist, or liquid-liquid equilibrium will exist, or how to define a mixture for a desired target properties. So what should be? We know the chemicals, we know the properties, but we do not know the compositions. So how to find those? We need also calculation methods. So having the database, having the models is not enough. We also need computational tools. And then the question is our model predictive? And what is the power, predictive power? The other one is regression and validation. And the other one is, if we have data, how much data do we have? And are the data consistent? So predictive power means safe extrapolation. Can we extrapolate out of the data we have? Interpolation is easier, but what we need is extrapolation. And if we can guarantee extrapolation, that will be predictive power. With the minimum set of data, measured data, how can we show predictive power? The next is regression, training, and which method to use. So usually when regression is done these days, people take, let's say, 75% of the data for training and keep 25% for validation. That can be good in some cases when you do not know what your groups or descriptors are to represent the molecule. But if you know your groups and descriptors, then if you do not take all the data, maybe you will miss some data that would represent some groups. So the application range will be smaller. So for some kind of modeling, it is not needed training and validation. Validation needs to be done with respect to interpolation and extrapolation. And also what regression method to use. Should it be minimization of least squares? Should it be maximum likelihood principle, which can also give an estimate of the uncertainty? Should we use machine learning, and so on? And finally, with the data, are the data well conditioned, sufficient, consistent? All these things need to be checked. So the steps that one can do, at the top you see the database. We have data of fixed number of compounds, properties, let's say 20 properties, but actually we have more than 20 properties. For each property, we have a number of chemicals. And if we count all the chemicals together, it can be quite large, 22,000 chemicals, for example. Then the data have been collected from measured published data. So we can put it in a location from which other people also can take if they want. So we can give a service to them. So that's the database. Once we have identified the property and the chemicals that have that property, we need to represent the chemical in the form of groups. So what are groups? We will see later, but these are a combination of atoms, not totally a molecule, but part of a molecule. So in principle, we have a total of, let's say, 424 functional groups. So they are more than one atom, less than the total number of atoms in a molecule. So how many of those groups are needed to represent a molecule? You see some examples in the second row. So every molecule then need to be represented by the vector of, let's say, 424 groups. Then we need to check the data. We need to check the consistency. We need to check the distribution. That means, are there molecules for which a property is given for every group? Or are there some groups that are not represented by any chemical in the database? Obviously, we cannot calculate the contribution of that. So all of these things we check in data analysis. After that, we decide how to do the parameter estimation. Should we do the maximum likelihood or minimization of least squares, where we fix the model expression? Or should we allow machine learning to tell us also what is the expression for the model? So that's the difference between machine learning and the conventional parameter regression, because in conventional we fix the equation and we only estimate the parameter. In the machine learning, we let the machine identify what kind of equation would be needed for the contributions of the same number of groups. So data analysis before optimization for regression of parameter is important. And as you can see, we can do different kinds of optimization. So the first step is experimental data set collection, representing the data as a set of groups and atoms. Model development, finding the expression for the model testing and validation, and model application and use. So one good criteria, at least for our modeling, is that we have, in our latest paper submitted to AICHE journal, we have modeled 25 different properties, and the selection criteria was that for any property, we should have at least 400 data points, meaning 400 chemicals. So our minimum was 440 and maximum was 1200 chemicals. So ranging from not very small to very large. And this is the set of 25 pure compound properties. We classified them as critical properties, normal properties, that is at the normal condition of temperature, pressure, standard properties also at the condition of standard condition, enthalpy of formation, and so on, environmental properties, and physicochemical properties. These are very common properties needed for many studies in product design and process design. Then the distribution of the data analysis, let's say. Under M, you see the number of data points. Under D, you see the distribution. So how is the distribution? The larger the D value is, closer to 1, the better. So we check all of these, And then once the data is acceptable, then we set the parameter estimation. So first, let's see how we represent the molecules. The small circles that you see in green, yellow, blue, red, these are different groups. And these groups can combine together through the valency rule of chemicals to give us a chemically feasible molecule, like you see 2-methyl-1-propanol. If we know the groups that are representing this molecule, and if we know the contribution of the property for these groups, those contributions are regressed, then we can calculate the property. If a group is missing, in some cases, we can also use connectivity index, that is the bonds that connect different atoms. And those index can be of 0 order, 1st order, 2nd order. So these are also our descriptors to represent the molecular structure. Once we have done that, then we need the actual model expression. So these are the model expressions, and we sum the contributions. So C to the power F, C to the power S, C to the power T, or superscript. They are the 1st order groups with F, 2nd order group with S, 3rd order group with T. So we add those contributions like that. And the summation of all those 1st, 2nd, 3rd order groups is 425. If it is a conventional regression, then each group has only one contribution. If it is a machine learning, then machine learning will make it a matrix or vector, and there will be more expressions needed to calculate this contribution. So let's see then the regression setup. On the left-hand side, you see the normal regression. We want to minimize the difference between the sum of squares, or we want to do maximum likelihood principle, and we want to get the value of the parameters, which are C, and then C to the power F, C superscript S, C superscript T. And Y is the values we have already experimental, so we can compare against experimental and calculate it. And every group has one contribution, so there are 425. If we do machine learning, we are doing some kind of maximum likelihood. So we are maximizing the objective function, but we have a negative, so it's going towards the negative direction. And to calculate the predicted value, you can see Y predict, we multiply a matrix K with a matrix W, and these are the weights and the covariance of the differences. And this can be quite large. So in principle, it can be NP times 425, where NP can be anything between 10 to 20. So which means that compared to the simple regression, we are using maybe 20 times more parameters for the machine learning. But machine learning is finding out the correlations for them, which we humans cannot find. What is the result of the modeling? If you see the figures on the right-hand side, they are red. And the more red they are, the better they are. And you can see that even for 1% error, the machine learning GCML is the machine learning model, is doing very well. If we look on the other hand, the GC simple model, we do not get that kind of performance for 1%, but for 5% and 10%, we still can get. So simple group contribution methods are good for up to 10%, but if you need higher accuracy, one needs to go to the machine learning. Then we can look at how well the correlation was. So you see the scatter plot where the On the x-axis is the experimental value, on the y-axis is the predicted value. If everything is on the diagonal, it is very good, except for a few points, which are the outliers, which after in a second iteration, we can take them out, then it is quite good. If you look at the figure on the right, which is the cumulative error, then you can see that nearly 80% of the data points are within 10% or even 1%. So the prediction accuracy is quite good. You can also see for toxicity, LD50, and the same cumulative plot. Let's see an example of calculation. We have remembered that the first step is to select the compound and the property. This is the compound, and we want to calculate the melting point. We have the model. We describe the groups that are needed to represent this molecule, both first order and third order. Second order is not needed. Then we retrieve the contributions of the groups, and then we put it in the equation and we calculate the value. So the first order value and the third order value is an improvement on the first order. And then we compare and check. The experimental is 318.95. We get 315.7. And other methods give 312. So that is how it works. If we want to estimate the uncertainty, if we have the covariance matrix and the Jacobian with respect to the parameters, then the equation that you see gives us also the uncertainty. And then we need to cross-check how good is the model and is it reliable. And here we need theory, because we know that according to theory, the critical temperature is always larger than the boiling point. If for any molecule, the boiling point is larger than critical temperature, then obviously that is not a good model, that's an error. Also, we have more data on boiling point than for critical temperature. So can we correlate boiling point with critical temperature so we can then predict more critical temperatures even though we do not have the experimental value? So this shows that our models actually thermodynamically are consistent. Also, you will see that in equations of state, the ratio of TC by PC is an important parameter. And if we make mistake in that, then the phase equilibrium will be in error. So we see that except for a few points, the ratio of TC by PC is predicted very accurately. And other correlations are also possible. And here is another correlation. Log P, we have values for log P for 1200 compounds, 12,000 compounds, sorry. And for water solubility, we have 2000. Can we use the log P values to predict the values of water solubility? If we can correlate that, we can get a bigger application range. So here is again one way of doing the property prediction in such a way that we can overcome the limitation of not having all the data points. And another example that also from a thermodynamic point of view can be checked is, for example, let's look at the curve. The blue curve is the heat of vaporization. The red curve is the vapor pressure. And this is a functional property. So we want to look at the heat of vaporization as a function of temperature, vapor pressure as a function of temperature. According to theory, vapor pressure must increase with temperature. It cannot go down with temperature. On the other hand, the heat of vaporization must decrease with temperature and should come to zero at the critical point, at the critical temperature. So from this figure, we can find out at the temperature where heat of vaporization becomes zero, what is the temperature? That temperature should match with the critical temperature. So even though we do not have experimental data, if this prediction is good, we can have an idea of the critical temperature. So these are also important checks one should do, because if they're wrong, then everything else will be wrong in the design of the product or the process. Finally, for some service role, here is a structure of the vitamin D molecule. What we see is that there are very few properties in the database, except for melting point. There's hardly any other property. We can calculate some more. Actually, this was more than 2 years ago. Now we can calculate many more. So this is a service role. Given the molecular structure, what are the properties we can predict? Another is fentanyl. Is a very dangerous chemical, is a poison. People have been killed through that. So what are the predictions of this molecule in terms of properties? You can see that melting point is not predicted very well, but we have improved this prediction. And also a molecule which is too big to be a refrigerant, but it can be used for many other applications. For example, in the hospital, for anesthesia, they use this kind of molecules. So if we want to predict those properties, give the molecular structure, get the property. So we have talked about the forward property prediction. Given the molecule or the mixture, calculate the property. Now the reverse is given the property, what is the molecule? That is the problem we call reverse approach, and we will highlight this reverse approach in webinars 3, 4, and 5. All of these involve giving the property value and finding out what is the molecule or the mixture that matches the property. So if we want to have a solvent or a refrigerant that is the best for a certain condition, we give the properties of the solvent, the refrigerant, or soap, or hair spray, and then we find out what is the compound of the mixture. So these are going to be covered in webinars 3, 4, and 5. So coming to the questions, when we synthesize, design, analyze a product and or process, we need properties. What properties? As we have seen, we need pure compound primary properties, we need pure compound functional properties, mixture properties, individual fugacity, activity coefficient, that are the phase equilibrium properties. How? We can do measurements, or we can do calculations on demand, which is the service, or the reverse, when we want to do the design of the molecules. And that's the list of references. So if there are some questions, I will take some questions now. Are there questions? You can show your hands. You're all experts in thermodynamics then. Okay. If there are no questions, I can start on time for the second lecture. But feel free to ask your question at the end of the second lecture. All right. I would like to get some questions. Oh, there is somebody who's asking a question.
Yes, number 191, I'm already unmute you. You can speak now.
Yes,
can you ask your question, please?
Yes.
Yes, thank you, sir, for your informative seminar. I had this one question, like suppose we, as you said, that the larger the molecules become, it becomes more difficult to predict their properties. So let's say like people working in biology, in biotechnology sections, always have to deal with biopolymers, such as enzymes, proteins, etc. So then they are quite large molecules. So are there any studies which have principles, or maybe semi-empirical, if the first principles become difficult, then in which they have predicted the properties for biopolymers? Thank you.
For polymers, there are property models, not first principle models. People are doing some molecular simulation with polymers, but with simple polymers like polyethylene, polypropylene, not biopolymers, not large, not even nylon kind of polymer, but very simple polyethylene, polypropylene, those kind of polymers. There are models. Remember that in case of polymers, one also needs to know the molecular weight distribution. So that makes it more difficult. But for a repeat unit of a polymer, that is like polyethylene, how many polyethylene would be in a polymer of 10,000 molecular weight? Those kind of things can be predicted now, like the glass transition temperature, the density, things like that can be predicted for polymers. But for proteins, enzymes, biopolymers, the problem is the data. There's not enough data to make those kind of models. So it's still experiment based. So these are empirical models. It's not that models are not there, but the models that are there are empirical. So in a way, they're not predictive. It only covers the data set that is given. So a lot of work is needed. Okay. Any other question?
One question is, does this method, yes, does this methodologies involve the
chirality of the molecules?
Yes.
That depends on the descriptors. The descriptors we have, we cannot take the chiral effects of the molecular structure, but we can take some isomers. Not all isomers, but some isomers we can take, but not the chiral. It depends on whether we can identify descriptors through which we can make distinction between those molecules. And also data is not, there's not enough data to be able to do those kind of modeling. Any more? Okay, I would say that, okay.
Another one from Miguel's. If we want to analyze an ionic liquid represented by an anion and cation, it should be considered as pure components or mixtures.
It depends on whether you want to predict the pure ionic liquid or the ionic liquid in solution. So if it is the pure ionic liquid, the method that we have described, we have also developed properties for ionic liquid, where we give the cation as a group, we give the anion as a group, and we give the functional part, the organic part as a functional group or a mixture of functional group. So we have the ions as well as the organic groups. Together, we can calculate most of the important pure compound ionic liquid property. But if it is in a solution, then the next lecture will describe that. It is possible. Okay? Okay, then we take the remaining questions. Please feel free to ask as many questions, and we will go to the next lecture.